Hello. Oh, great. Well, welcome everyone to the session. I guess we're going to just get going. First of all, I want to introduce myself. I'm Praveen Vimalapalli. I'm a director at AT&T. Again, outside work. I love to hang out with my family. I'm an avid motorcyclist. I used to be in California. Now I'm in Texas. It's not that easy, but then I make it well. So we're going to talk about some of the stories, especially a network-related story that we have gone through at AT&T. So it'll be a good one. Again, no introduction needed, but I will do that honors again. AT&T is one of the largest telecom companies in the North America, right? We have a huge history in the books. The whole idea of telephone getting invented, and we got Graham Bell getting patented, all that history. We have I'm not going to dig deep into the history. Not going to bore you guys much, but think of a company. We are a telecom company, but I also want you to think about we are also the first inventors of C++ in our labs. You talk about Unix, you talk about Corn Shell. We were also the inventors of a language called S, which is a predecessor of R, again, back in the days. So technology is also in the nerves of AT&T, and we continue to pace in that, innovation in that space, right? Quick background. I want to talk about a few things, again, just for context-wise, right? We were a heavily on-prem, data center company. We have humongous amount of data centers. If you guys attended last year, at the same session, I talked about our migration of all the data elements, all the applications that we had on-premise, and how did we plan to choose to go to cloud using some of the public cloud providers. Again, most of this is public news. We chose Microsoft. In 2019, we talked about, hey, we're going to start using non-network related workloads, some of the OSS, BSS systems like billing systems, care platforms, and then slowly, in 2021, we also announced publicly talking about moving network operator services into the cloud with Microsoft. So we have a huge partnership with Microsoft. We are working on actively building a hybrid environment where we can operate our core networks, including our on-prem infrastructure and Azure cloud infrastructure, right? This is about running the network itself, the core network. Again, this is the slide I wanted to talk about is last year, if you guys have missed it, we put all the numbers out there. We have a massive Hadoop environment, which we were about to, it was a large use case. So we were able to successfully migrate, I think JP is here in the crowd. So we talked about it last year of how we migrated our Hadoop environment back into the cloud, the entire journey, how we set up from ground zero and everything, right? So there's a lot of value proposition. Why did we do it? Obviously, just like most of you guys are here, we did it first to, be more optimized in the cost, be more faster in the cloud, spin up infrastructure as we need it, use dynamic compute as we are in the cloud. And obviously, we got rid of a lot of data centers, right? We sold everything on the ground pretty much and by investing into the cloud infrastructure, right? So obviously, there is a lot of details in here. I'm not going to talk, but again, a quick overview of our migration that we talked about. This was our enterprise Hadoop environment. We have one, when you think about it, for AT&T that we talked about here. So today, in the context, I talked about AT&T and our larger idea of going to the cloud, how we invested our network and non-network workloads to be migrated. Today, in this session, we want to talk to you guys about a specific network-focused application where we process billions of events daily, and then we ingest all that data, we process, and just to give you a quick metrics, just to give it, at least this is very application specific. So think about an application, gathering data from the network elements. Think of all the things you have on your cell phones, all the network. Every piece of information is coming live every second, and we capture about like 17 billion plus events And then similarly, this is a situation on premise, right? How we were doing on operating that specific environment. We talk about, obviously we're processing a lot of data. We were using about 6,000 to 7,000 CPU cores on premise. If you do the math, these are massive amount of infrastructures, GPU heavy machines, processing a lot of real-time data. So there was a lot of infrastructure spread out, right, to run these applications. This is one application, just to give you an example. And just as you guys all do, right, we process all the data to build some KPIs, obviously, which are valuable to run the business, right, or which are valuable to run and optimize our network planning situations. So again, we were running on-premise almost to be exact 32 or so hours. I mean, just imagine, you process all the data, run on this massive infrastructure, and at the end of the day, it takes you 30 so hours to process the end product, right? So that any of the users or the analytical communities can actually use and leverage that data set back then, right? So this was the story of us on-premise, highly, scaled out environment, uses a lot of infrastructure, and then at the end of the day, takes about, at an average, if no issues, 22 hours, there is always some issues with the, Kafka feeds. Yeah, we talk about 30 hours, right? Just to process a daily record. And this specific use case is only about analytical processing. We have other workloads too, but we're talking about analytical workloads. This was the, situation back then. And what we did after that fact, right? In the process of migrating to Databricks, right? With all the things we did, Akshay is going to talk about it in detail, about what are the best practices we followed, and what are the computing, protocols we kind of adhere to, and all that good stuff. And then at the end of the day, this is what we ended up to be, right? Right now, we run this application in the cloud. We have substantially reduced about 30% of the environment size, right? And then if you look at the CPU cores, we used to run about 6,000 to 7,000 CPU cores. Now we dynamically use only about close to 1,000 for running our analytical workloads, right? And last but not least, think about the hours. So we have reduced almost our 22 to 30 hour workloads that used to run daily to 8 hours. This was one of the amazing wins as part of this migration. We were able to optimize code. We were think of all the code that was written in MapReduce and basically leveraging Scala. Now everything runs on Spark and Scala together. Again, there was a huge cost savings when you compare. I just want to emphasize on one thing. I talk about the 30% cost reduction, right? If you look at it, let's say you're spending, let's say $100. So 30% is about $30. But I'm talking about a platform that runs on millions of dollars. So if you look at that scale, even if it is 30%, 30% of so many millions is quite a bit of millions, right? So the context at large is very beneficial for us, and we were able to show a very nice story around this. I went on a little faster, but again, this is the story. This is the application we want to talk to you guys today. And I'm going to introduce you guys to Akshay, who's going to walk you through the do's and don'ts as you do migrate some of these type of workloads which are heavily network oriented or heavy events based applications, right? Akshay, take it over. Yeah.
Hi folks. Okay. So thanks Praveen. So hi folks, I'm Akshay Sharma and I work at Databricks under Professional Services umbrella. And over the course of next few slides, we will discuss some more technical aspects of our migration journey. And we will start with a high-level solution architecture. Then we will discuss some of the key challenges that we faced and how we rectified them. Then we will discuss a bit more about some of the best practices that we followed in the entire solution. And finally, some of the key takeaways and some of the key points or learnings that we got from this entire exercise. So basically, to start with the solution architecture, in this entire solution, from start to end, there are like various components involved in it. There is Kafka, there is some streaming flow servers, there is ADLS storage accounts, there is Databricks, and each and every of this component has their own responsibility, and each of these components enriches your data in some way. So we'll start from left to right, and we will discuss each of this component. So in our case, the base data that we are receiving is basically coming as multiple data uploads from a variety of different sources. In this, each upload, we are basically getting a clubbed information or cluttered information of multiple events. By events, I mean since this data is more of a networking nature, so the data that we are getting is of events, multiple events in a single upload. So the first order of business we first streamline all these uploads into a single component, which in this case is Kafka. So this Kafka acts as our single source of truth for our remaining of the pipeline. So now all my data uploads that I am getting from multiple data sources are singly pointing to this Kafka component. And now this Kafka component is my input and my single source of truth for my remaining components. So once my data is pointed to Kafka, then the second component is a custom streaming flow server. Now this streaming flow server consumes data, or in our case, it's event data, and performs two major responsibilities. First, it performs some basic elementary data quality checks, like which data to retain and which data to simply discard. It filters out bad data, retains the good data. And secondly, since we are getting a clubbed information of multiple events, our business logic demands that each event should have a separate processing logic associated with it, and each event is going to be processed separately. So the second responsibility of the streaming flow server is it simply parses those events and segregates it into multiple events. And these multiple events are what basically means that these events will be my final processing data that I want to process. Now, once the streaming flow server processes this into multiple events, then it pushes them as separate Kafka topics, and like each Kafka topic pertaining to one event, and then comes into the play is this Kafka connector component right next to the streaming flow. This Kafka connector basically runs over a multitude of Kafka clusters, and we do have like more than 2,000 plus Kafka active clusters. This Kafka connector subscribes to this Kafka topics published by the streaming flow, and then pulls the data and exports it into Azure Data Lake Gen 2. And this ADLS Gen 2 is our input for our final batch processing. The uploads that we are receiving from the source, they are in the order of some 10 to 15 million uploads. And this data that is going to serve as our input into ADLS Gen 2, this is around like 13 to 15 terabytes of data. And this is for ever increasing data. And this entire data that we are discussing about, this is 1 day's worth of frequency. So once my input data is in ADLS Gen 2, then the Databricks component takes over and performs the final business processing of business logics, right? So it performs some more data quality checks like deduplication of data, filter out null values, filter out some obviously bad records. And after filtering out those records, then it starts with the final processing, applying business logics. And since our data is more of a time series nature data, our business logic heavily revolves around applying business or time series correlations. So that's the business logics that Databricks applying data quality checks, and all of these are applied by a series of SQL transformations, your usual SQL joins, distinct operations, set, where, etc. So Databricks process all this data and writes the final version of your output data into ADLS Gen 2 in a separate container. So ADLS Gen 2 is utilized twice, once for receiving input for our batch processing, and then finally for writing the final consumption ready data. And once it writes this final data, then this final data is later consumed by some BI tools for extracting key insights for some business users. And this data is what you call production ready data, and like it requires no further transformation. It can be consumed directly as it is. And in the mid of processing, an interesting fact is that whatever data we are getting as input, which is close to like 15 terabytes, in the mid of processing, the temporary storage or the temporary size of data increases by 10 times. So it becomes close to 130 to 150 terabytes worth of data. And this is the data that we process in a single day. So in this entire architecture, the uploads that we are receiving are in the order of millions, some 10 to 15 millions. However, when we write the final output data into ADLS Gen 2, then that is in the order of billions, 45 to 15 billion of records. So this is because of the extensive processing that we are doing, applying the transformations. So this is an overview of our solution architecture, and this comprises of several components. And over the next slide, we will discuss about some of the key challenges that we faced and how we rectified them, especially around the Databricks component of it, because that component is the one that is doing the actual heavy lifting and doing the actual real processing. So on the challenges part, our challenges can be like broadly classified into three categories: on a code level, on an infra level, and finally on a data level. So the base initial solution of this entire project was written in MapReduce, legacy MapReduce code written in Scala. And since our data is of a time series nature, our MapReduce code heavily employed usage of loops, for loops, while loops, etc., to maintain the state of time, right? So when we were first transitioning from MapReduce to Databricks Spark, the first step that we took was migrating it to RDDs. Now RDDs, you might be familiar that it is a base form of data frames and does not require that much of a schema information. So while we were transitioning from MapReduce to Spark, then just a couple of tweaks, making your functions, registering them as UDFs, and MapReduce code was transitioned to Spark RDDs. This was fairly easy compared to the effort that took for migrating to data frames, but migrating to RDDs does provided us a significant boost. But when we carefully profiled it and debugged it, we found that there are still a couple of key issues that needs to be addressed, specifically around high amount of network latency and high disk I/O, which were like completely gone when we moved to Spark data frames. In Spark data frames, the parallelizing capability of data frames was very efficient, and compared to RDDs, it was far more performant. So when we moved from MapReduce to data frames, and since our code was more of a design of row by row processing, in data frames we are doing more of a column level processing. So this was a big design change for us, and it took like substantial effort to migrate to data frames. But thanks to the effort and dedication of the entire team, we were able to pull it through. And once our code migration was done, then we started our like end-to-end pipeline testing. And we came across a few more issues The first one of them was storage account API rate limits. Now, typically, majority of the storage accounts, no matter which cloud provider you use, has a certain rate limit enforced on their servers. What that basically means is there is only a limited number of requests per second that you can request to storage account. And this request can be anything. You can be reading files, writing files, creating files, etc. But since we are processing a large amount of data, and that too parallelly, we are processing multiple events parallelly, so even this high limit is getting exceeded in the mid of processing. So when we analyzed it, we found that no, this rate limit is not working for us. We need to somehow stretch it. So immediately we raised this issue to Microsoft, and thanks to their prompt response, they increased the storage account API rate limit, and this bottleneck was removed, and our issue was alleviated. And with this, our pipeline was really stable and far more performant than its draft version. And then finally, over the course of several next iterations, we keep finding more and more data quality related issues. And these data quality issues were regarding basic issues that you find in your everyday ETL projects, like getting duplicate data, getting null values where they are not supposed to come, date time parsing issues, etc. So since we had a large amount of data, finding it in one go was not easy. So it took us several iterations, but by the end of the release, we were able to solve majority of these data quality issues. And with all these three challenges rectified, our pipeline was what you call the first level of production ready pipelines. And finally, the pipeline was working stably without any errors. However, from a performance point of view, it was good till the end of these challenges. But there were a couple more things that we did to improve our performance. The most prominent of them was your task orchestration. Now, when we hear the term orchestration, we basically think that orchestration just means grouping of events or the order in which your tasks are going to get executed. But in this example, we will see that orchestration, while true that it is grouping and ordering and execution of events, it is also a very efficient approach to optimization. Now, these 5 blocks you see adjoined with arrows, this is a classic example of Databricks multitask workflows. Now, what Databricks multitask workflows means is, in a workflow, you can easily manage dependencies between multiple events, as well as you can easily automate your end-to-end pipelines by deciding which task to go first, which task to go next. So, in this example, we see that there are 5 blocks, and these 5 blocks basically corresponds to 5 of our events. And rather than saying events, we can say these 5 blocks corresponds to processing logic of 5 distinct events encapsulated in some artifact. And in this case, our artifact is, let's say, Databricks notebooks. So this 5 blocks corresponds to 5 Databricks notebooks, and our end goal is to simply execute them within a workflow. So let's say each of these 5 events have their own associated execution time. Let's say A is taking 30 minutes, B takes some 20 minutes, C is taking some 60 minutes, D 15, and lastly E is taking some 5 minutes. Considering that I am going to execute all of these events sequentially, one after the other, it is taking some 130 minutes in total. When we carefully analyzed each of this task or event and saw that whether the dependency flow that we have created, which right now is sequential, is really needed or not, as well as what is the execution time of each event. After carefully analyzing these metrics, we thought that maybe this workflow can be modulated into this version. Now, this is obviously a much more simplified example of our actual workflow. Our actual workflow is far more complex and contains close to 100 plus tasks. But this example will convey the message that orchestration will be able to optimize your workflow heavily. Now, in this case, you can clearly see that B and C are going to be executed in parallel. And compared to the previous version, where B and C were executed sequentially, we analyzed that maybe B and C does not have a dependency on each other. They are simply dependent on A. So this graph shows that B and C in this case, rather than executing sequentially, are simply fanning out of A. Now, to avoid cluster conflicts, we simply say that B is executing on a separate cluster, A, C, D, and E are executing on a separate cluster, and these two branches are running in parallel. So if you look at it, out of your entire workflow execution time, which in previous case was like 130 minutes, since C is taking longer time than B, B's execution time will be completely gone out of your workflow. And this does not require any code change or library change. It's just a carefully thought of workflow. So in this case, the total time is 110 minutes, since B's execution time is gone out of the pipeline because B is working parallelly to C. Now, this might seem a very obvious thing to do, but this is one of those techniques or methodologies that is often neglected and can give you free performance marks. In our use case, this easily reduced our execution time by 40% or so. In our use case, let's say we have 10 events, 9 of them are like small events and one is a very critical or time-taking event. Then we analyzed the dependency and saw that maybe those 9 events need to execute after each other, but maybe this one event can execute simply individually. So we branched out into 2, executed the 9 events as a part of first branch, executed the big event as a part of second branch. And doing this simply reduced our time by lot margin, right? So this was a very critical optimization for us, which technically speaking not is a optimization, but rather simply modulating the way you are orchestrating your workflow. Aside from this also, there were some practices that we have followed. Strictly speaking, they are best practices, but these are the practices that literally gave us a huge performance boost. Those are cache and persist, Databricks runtimes, data distribution, Photon. Now, cache and persist are a very commonly used method for optimizing your Spark workflows. What they basically means is you simply cache a data frame into your memory, and in case you want to later reuse it, then you can simply pull it out of the memory and reuse it without calculating again and again. Especially in case of for loops, when you are using data frames, this becomes a very critical optimization piece. However, there is a catch. When we are persisting a data frame, usually what we don't do is unpersist it. So considering our workflow example, if you have 2 tasks, task A and task B, let's say in task A you persisted a data frame, at the end of task A you didn't unpersist it. What will happen is that data frame will be persisted in the memory, and even the task B, which is running on the same cluster, what memory should have been rightfully available to task B, not all that memory will be available. A small chunk of it will be occupied by the data frame that we persisted in task A. And this will not only not enhance our performance, it will actually degrade our performance. So cache and persist are supposed to be used for optimization, but they are supposed to be used wisely. Now the second is Databricks runtimes. When we initially started our migration, we started with runtime 9.1, then we eventually moved to Databricks runtime 12.2, And then we finally moved to 13.3. And with each runtime upgrade, we saw a significant boost in performance without any code changes or so. The reason behind that is with each Databricks runtime, not only new features are added, but existing capabilities are also enhanced based on the multiple feedback that we receive from the users. So every time a new Databricks runtime comes, we should really evaluate it. If it fits our use case, then we should try to migrate to that particular runtime version. Third is data distribution. Now, data distribution can really refer to many things. But in this particular case, what I want to especially emphasize on is data skew. Data skew is basically the uneven distribution of data, and data skew can be a real performance degrader. For example, in our use case, the skew was something like this. In this graph, you can clearly see that my entire processing is pretty much going to only one executor, which is the second one. And compared to that, my remaining executors are almost sitting idly. This is a very good example of data skew. And what this will result into is that your cluster utilization will drastically go down, and the total time taken for processing will be basically the total time taken by executor 2. So to rectify this, Databricks provides, or Apache Spark in general provides, from Spark 3.0, AQE, Adaptive Query Execution. Now, Adaptive Query Execution has several features, like it propagates null relations, it dynamically handles skew data, it coalesces some small partitions into a large partition. But in this case, AQE was able to handle it to a good extent, but it's always a good practice that rather than applying patches, we should drill down into the root cause of the issue, right? So in this case, when we drill down into the data, we saw that when applying some joins, some of the join keys are getting a high number of duplicates. And because of those duplicates, my entire processing is going on just one executor. Once we deduplicated this data and then initiated the processing, then our skew was gone. Our data was far more evenly divided among the cluster. And obviously, the pipeline was performing far better than before. So that's data distribution. And lastly, Photon. Photon is perhaps the simplest way of optimizing your workflows. Whenever you are struggling with performance, the one thing that we should definitely try, go to the cluster page, edit the cluster, enable Photon, and just run the same workflow again. Without any code changes, without any infra changes, without any library changes, there is a very high amount of chance that this Photon will simply optimize your performance without any manual effort on our part. The reason behind is that Photon is a native, Databricks native engine simply for optimizing your SQL queries or SQL-based workloads. Now, since data frame follows the SQL paradigm, especially in cases when we have long-running queries, like at least more than 10 seconds, and if we have workloads that are running on large data sets, and if we have workloads that are especially on SQL, for SQL, Photon has the maximum coverage. And if we are not using any custom UDFs, because SQL UDFs or custom UDFs, Python or Scala, are still a black box for Photon. So if we are meeting these conditions, then we should definitely try Photon, because Photon will, in this case, enhance your performance. So this is a classic example of Photon. This is how you will visualize whether your query has been affected by Photon or not. On the left-hand side, you see a SQL query plan that is like feature-rich by Photon. And in this case, you can clearly see that the stage is taking 5 milliseconds at the top right corner. compared to the non-photonized version on the right, that is running on your normal Spark, which is taking close to 188 milliseconds. So in this case, this is close to a 40 times boost. So Photon is one thing we should definitely try whenever we are struggling with your performance issues, right? So in conclusion, these are some of the key takeaways and learnings we got from this entire solution. And they are also applicable as general recommendations, right? It can be applied easily on every other use case as well. And that is stick with data frames. So while we can do several other kinds of processing, like we were doing MapReduce, we were doing RDDs, when we are executing something on Spark data frames, we don't need to do any manual fine-tuning to parallelize it. Any operation performed on Spark data frames is by default parallelized into your entire cluster. And thanks to like Spark's capabilities, it does a best try effort so that your distribution of your processing and data into your cluster is as even as possible, right? This is especially true when we are doing Spark provided out of the box native functions. These functions are far more optimized to run with data frames compared to the custom functions that users write. So yeah, data frames should be leveraged as much as possible. While it might not always be possible to just use Spark data frame functions, we might need to use custom UDF somewhere, but try to stick with data frames and functions as much as possible. Second is your storage account. Now, whenever we are running any pipeline, we should make it a habit to actively monitor the storage account logs appearing into your pipeline, right? In case if you are seeing seemingly throttling behavior, and if you are seeing that maybe some unusual messages, error messages are coming into your pipeline, then we should definitely consider turning on some few knobs on your storage account because they can really hamper your performance. So storage account logs should be actively monitored. And finally, data quality. Now, data quality in general is also imperative to your business logics, but data quality issues can really affect your performance as well. So rather than waiting till the end to apply the patches, we should actively try to identify these data quality issues as early as possible and rectify them at the root. This will ensure that your pipeline later down the stage will run seamless and smooth. So these are some of the key findings that we got from this exercise. And these things can be applied for every use case, not just this particular one. They are not like very complicated or very special, but these are the general things that we can try for every other problem that we are facing. So I hope this session was fruitful for everyone, and thank you for joining us today.
Great. Thank you.